Okay, folks, so we're continuing on in our introduction to line integrals, and we're going to work our first example now, where we're given a particular function, the cube root of xy, and we're asked to integrate a line integral over this function. So an interpretation of this is what I've mentioned before, where we're going to be finding the area of this green curtain here that hopefully you can see. This green curtain right here. And the way we can think about this is that we've got our curve C, which comes from the xy plane. Here's the xy plane. We've got our curve C here, which is in this case is just the parabola y equals x squared. And this is going to go from the point 0, 0 to the point 1, 1 following this parabolic path. And so you can see down in the xy plane here of this curve in 3 space, there we've got that, there's that parabola, right? There's the x-axis, there's the y-axis, there's that parabola. Let me make that a little bit, there's the parabola y equals x squared. And so you can see what we're looking at computing here then is the area of this green curtain, which is formed by looking at the curtain, the green curtain between the function, which I've sketched in this kind of off-colored red here. This is our function f of xy. That's the cube root of xy. Is that right, xy? Yep, that was the cube root of xy. There's our function here. And we're looking at the region formed between that surface and the curve sitting here in the xy plane. So that's what we're going to be computing. So let's go ahead and do so. So I'm looking at our steps that we talked about last time, where we need to come up with a parameterization, we need to compute the speed component, and then we go ahead and set up the integral that we want to evaluate. So let's go ahead and do this. The first thing we need is we need a parameterization of C. Let's do that in a thicker marker there. So we want a parameterization of C. Well, I think there's a really natural choice for this. I'm going to use the parameterization r of t is equal to, and I'm going to just pick t for the x component and t squared for the y component. This is kind of the most natural choice for parameterization when you've got a function of where you've said y is some function of x. You pick the x coordinate to just be t, and then t squared. Unless you have some other choice, maybe you've got like a circular region or something like that, a circular curve, this may be the most natural parameterization to pick. Of course, we've already learned, and please do not forget this, it is essential that you remember the domain of this parameterization, and this is going to apply from 0 less than or equal to t less than or equal to 1. One thing I would always stress that you do, especially if you're feeling a little rusty with parameterization, is always check to make sure you're at least including your endpoints here. Notice, for example, that r of 0 here does indeed give me r of 0 does indeed give me the 0 vector, 0, 0, and r of 1 here does indeed give me the final endpoint, which is at the vector 1, 1. Okay. So we do have a parameterization. This is a correct parameterization, but I do encourage you to check those, right? A lot of times it's easy to make a mistake, and it's oh so easy to catch a mistake if you just check it real quick. Okay, the next thing we said to do in this procedure is to go ahead and compute that speed component. So I'm going to compute the magnitude of the derivative of our parameterization. Okay. Well, if we compute r prime of t, that's the function 1 comma 2t, and if we go to compute the magnitude of this, would be the square root of 1 plus 2t quantity squared, which is the square root of 1 plus, I'll just write 4t squared. So now we're ready to set up our actual integral for computing. Again, this is the line integral in its kind of most simplistic form, and it's easiest to think about it as a line integral in that way. But as soon as we want to actually begin evaluating it, we need to write it in this form where we utilize our parameterization. So 3, let's go ahead and give our integral. So the original integral, the line integral over the curve C of our, let's see here, I think we had the cube root of xy ds. Well, that's equivalent to the integral from t equals 0 to t equals 1. Those were our endpoints for the parameterization. Those are those endpoints for the parameterization. And let's see here, the function can now be rewritten as the cube root of, and then let's see here, we're going to replace x with x of t. So notice here by position, x of t is equal to t, and y of t is equal to t squared. So we'd have t times t squared. That should look a little more like a 2 there. Let me switch this to the larger font. The cube root of t times t squared. And then we replace the ds with the magnitude of t, which we said was the magnitude of r prime of t, which we said was 1 plus 4t square rooted dt. So this is the integral we need to compute. Well, this cleans up pretty nicely as the integral from 0 to 1 of just t times the square root of 1 plus 4t dt. And folks, I dropped the squared here. Let's see here. That should be squared. That should be squared. And if we integrate that, you could do a u substitution on it if you like. But let me see here. We'd have an 8t, so we need to divide by 8, and then 2/3. So I think this comes out to be 1/12 times 1 plus 4t squared to the 3/2, evaluated from 0 to 1. And so then if we evaluate this at the limits of integration, we would have, let's see, 1/12 times, if we plug in a 1 here, that would be 5 to the 3/2 power, minus, and if we plug in a 0 for t, that would just be 1 to the 3/2 power. And that cleans up to be the 5 square root of 5 minus 1 over 12. And you can check that arithmetic there. So folks, don't lose sight in the, in the computation of the integral, what we just did here. We had our original function that we wanted to integrate over this particular curve. And so in this case, what we're saying is we could take this surface, which is depicted here in the red curve, or the salmon-colored curve, and but we only want to evaluate sort of the area of the curtain formed between that surface and the curve y equals x squared in our xy plane there. And so what we've computed here in doing this computation is we found the area of that green curtain. So folks, what I'd like you to try is I'd like you to go ahead and do number 10 on your own. You'll have to come up with a parameterization of this curve. It's not too hard of a parameterization. Think of a line. Be kind of judicious in how you set it up, because you might make the integral easier for yourself. But go ahead and evaluate that particular line integral. And if you get stuck, or if you want to check your answer, I've got the solutions down at the bottom. And this concludes this pre-work for our section 17.2.